Thanks everyone for letting me have a chance to speak. If Eugene is feeling not like a developer, then I'm 7 steps lower on that totem pole, having contributed very little aside. But I thought this might be an interesting little nugget for people to chew on here. My name's Josh Rackers. I'm a Truman Fellow at Sandia National Labs, and I also sort of split the difference between the MD world and the QM world. So just a quick, I guess, reintroduction to the Hellmann-Feynman Theorem for those who may not have thought about it in a while. If you want to calculate the force on an atom in any molecular cluster, there's basically 2 ways that you can do that. The first is the typical way, which is to take an energy derivative, and this is the way that virtually every quantum chemistry code does forces. But there is a second way, and the second way is to use the Hellmann-Feynman Theorem. And the Hellmann-Feynman Theorem just says that if you have the derivative of the energy with respect to any parameter, you can use this formula right here to calculate that derivative. And importantly, you can use this to calculate the derivative of the energy with respect to changing coordinates, and that gives you a route to calculate the force on any atom. And the thing that's really cool about the Hellmann-Feynman theorem is that whenever you apply this, you just end up with Coulomb's law, right? So away goes all the messiness of quantum mechanics, and you can calculate the force on any atom directly and accurately from its surrounding electron density. And just as sort of an aside, I think this is what makes the Hellmann-Feynman theorem really cool. It's kind of the link between the weird, complicated world of quantum mechanics and the world that we understand and think we know of classical mechanics. Okay, so why do I care about the Hellmann-Feynman theorem? What's the motivation? So like many of you here, I want to build machine learning models. And in particular, I want to build a machine learning model for electron densities. So I want to replace time-consuming quantum mechanics calculation with a neural network. And crucially, what I'd like to do is I'd like to do this not for small clusters of atoms, but for very big things the size of a protein. Okay, so why does this tie into the Hellmann-Feynman theorem? In short, I want to use the densities that I predict from these machine learned models to calculate forces. And so I set out to kind of understand this problem of can we use the Hellmann-Feynman theorem to calculate forces? And the short answer I get from everyone when I ask this question is no. The dogma in computational chemistry and quantum chemistry is thou shalt not use Hellmann-Feynman theorem forces because they are junk. And in particular, they're junk for 2 reasons. The first is we often or almost always use incomplete basis sets, and they're also junk anytime that we use a non-variational method. In other words, anytime that either of these conditions is not met, then the Hellmann-Feynman theorem has error terms that are not calculated. What I'd like to show you are sort of 2 little shreds of evidence, 2 little pieces that show that I think that both of these conditions actually can be overcome. So first, I'll show you that we can develop basis sets that can be optimized to satisfy the Hellmann-Feynman theorem, and then show you a really cool result, which is that you can get coupled cluster Hellmann-Feynman theorem forces that are really quite accurate. Okay, so the first slide I'd like to show you here with results is everything's going to be about this test system of the water dimer. And I'd like to show you comparison between Hellmann-Feynman forces and energy derivative forces. And everything on this slide is SCF. So if you do this comparison with a relatively small basis set, so in this case, a DZ basis set, you can see that Hellmann-Feynman theory forces are junk. They are the blue arrows in this very modern diagram here, and they're completely inaccurate. Let's see what happens if we go to a very large basis set, a QZ basis set. Still, they are junk. So even whenever we go up to what's, by most standards, a very large basis set, we still are not close to converging to the energy derivative forces. We have to go all the way up to 5Z to get anything that's even qualitatively close to correct, where the forces are going in the correct direction. And again, this is for SCF. This is for a variational method, so we're just looking at the completeness of the basis set. But the good news here is that you can actually develop a basis set that's optimized to fulfill the Hellmann-Feynman theorem. So the agreement here isn't perfect, but working together with some friends in Spain who have thought about this a little bit, you can develop a basis set that's much smaller than these giant 5Z basis sets that are necessary to fulfill it normally, and actually get pretty decent agreement between the energy derivative forces and the Hellmann-Feynman forces. That's pretty cool. We can sort of extrapolate, or it's not extrapolate, we can get a handle on the basis set error. Can we use this for non-variational methods like coupled cluster, what I want to do in my machine learning application? The short answer is pretty much yes. So using that same basis set I showed on the last slide, here's the same calculation but done for coupled cluster. And you can see that qualitatively our forces here are in the right ballpark. And if you bump up everything by one to the next level of size and basis set, you can get pretty close to quantitative agreement between the forces from Hellmann-Feynman theorem and from energy derivatives. So I think this is pretty cool. It's saying a lot of things, so I'd like to just briefly give you my take on what I think these little tests are showing. And they're just suggestions, right? This is not an extensive test. But the first is that I think that we can make Hellmann-Feynman forces work if we optimize basis sets for them. Dunning basis sets and the like were optimized on energies. There's no reason to believe that they should be good for Hellmann-Feynman forces. Another thing that I've noticed is that the forces are most sensitive to every atom's own core basis functions, and would love to know people's ideas for if there are good ways to solve that problem. Hellmann-Feynman forces for intermolecular interactions are almost exact. For variational methods, these forces can be made exact if we use big enough basis sets. And most interestingly, I think, for non-variational methods, if the method is good enough, meaning if the error terms in the amount that the method is not variational are small, then these forces can be very, very good. So I'd like to leave you with sort of a kind of semi-provocative slide here to think about. Hellmann-Feynman theorem forces are just as valid as energy derivative forces. There's no reason that one should prefer one over the other. In the end, if you had a perfect method, they should be equal to each other. And so that leads me to a couple of thought experiments. The first is, can we use Hellmann-Feynman forces as a measure for the error, or the amount that a method is not variational? In other words, how far is, for instance, coupled cluster from a full CI answer? Second, are Hellmann-Feynman theorem basis sets a better measure of basis set completeness than typical energy convergence criteria? And are there applications for which actually using Hellmann-Feynman forces might be better? So with that, sorry for going a little bit over and sorry for the technical difficulties, but I'd like to thank my friends in Spain for their help developing these basis sets, Andy for contributing some code that helped test these things, funding. And of course, if you're interested in working at a national lab, or if you're interested in ML for quantum systems generally, please feel free to get in contact with me. Thanks.